So hi everyone, I'm Kelemua and Tesfaye, and this is a summary of some of the research I've collaborated on last year with Dr. Allison Henrich, Alexandra Ionescu, Brooke Matthews, and Isaac Ortega. So we were interested in investigating knot mosaics and creating a game. And one day while playing with the tiles, we noticed it was really fun and challenging trying to create growing, suitably connected mosaics. And drawing from the framework of Tetris, we created the game Knotris. So the goal of the game is to create and clear as many suitably connected rows for as long as possible without placing a falling tile below the height of the 6x13 board. And we wanted to study the probabilities in the game to give us insight into how to improve the game design as well as inform our gameplay strategies. So I'll begin by going over some terms. A mosaic is a contiguous arrangement of knot mosaic tiles, of which there are 11, and we've organized the knot mosaic tiles into 4 equivalence classes on the right by rotation equivalence. And a Roman Knotris is a 1x6 mosaic. So while fiddling around with the physical wooden tiles that we had, we found that the 7-tile bag on the right lent itself to the most natural gameplay. So we chose the game bag to be a shuffled bag composed of 3 of these 7-tile bags, as you can see on the right. And once all the tiles are picked by the player from the bag, the game bag resets itself. So a connection point is present along any edge of a tile that a strand passes through. And here they're indicated by red dots. And a tile is suitably connected if each of its connection points touches a connection point of a contiguous tile. So in our game, a row can be either internally or externally suitably connected. A row is internally suitably connected if each of its connection points on an internal edge is satisfied. And below are examples of an internally suitably connected row, as well as a row that's not internally suitably connected. And we defined a row to be externally suitably connected if it's suitably connected to the row above as well as below it. But for the purposes of the game, we reduced our definition to only consider the row above. So, and finally, a boundary condition is the trace of the external edges of a tile, row, or hole, and it's represented by n tuples of 0s and 1s, where a 0 corresponds to there not being a connection point along an edge, and a 1 corresponds to a connection point being present. And here are just some examples of boundary conditions of tiles, a row, and a hole. In order to gain points in Knotris, we want to make suitably connected rows that can meet particular upper boundary conditions. So we were curious about how many unique rows could do so, as well as, and this could tell us how many ways we can clear a row, and if clearing a row is possible given assumptions about the tiles we have. So initially I tried to figure this out using a single 7-tile bag. And since Knotris has a 6-tile wide board, pardon the noise, I just moved. Since Knotris has a 6-tile wide board, we made 4 6-tile bags by omitting 1 tile of each tile type from the original 7-tile bag, as you can see on the right. And to see how assumptions about our bags impacts the sort of rows we can make and the probability of filling a row, I made the filling a row algorithm, where given a tile bag, we assemble all the rows using all possible permutations and rotations of tiles from our bag, then remove all the non-suitably connected rows, and outputting the lower boundary condition of each suitably connected realizable row and its respective frequency. And then I repeated this procedure for all 4 of our 6-tile bags. But the 6-tile bags we defined earlier don't capture all the 6-tile combinations that you might encounter during gameplay. But here are the aggregate outputs of the O bags. So it's important to note that the aggregate outputs of the O bags is equivalent to a single 7-tile bag. And you can see in this plot that the x-axis is the number of unique rows and the y-axis is the boundary conditions. And this isn't the full list of boundary conditions, but because of symmetry, I've only displayed one boundary condition from each symmetric pair. So since I'm displaying like 1, 1, 1, 0, 0, 0, I won't display 0, 0, 0, 1, 1, 1. And by unique, I mean that it's visibly unique to the player. So tiles from the same equivalence classes aren't considered unique. And to get that results that were more reflective of what the player could encounter, I adjusted my Python code so that it would be more flexible about the types of bags that you could consider. And then I applied the algorithm to the game bag. And I got this output. So the number of unique rows that can be assembled, or this is a plot of the number of unique rows that can be assembled given the game bag versus a 7-tile bag. And you can see that the boundary conditions that are most easily realized, as well as the frequency, varies widely from the 2 different bag types. So it was helpful to take the extra step to adjust the code. And since we wanted to develop strategies for gameplay, we studied the probabilities of filling holes. So in order to begin, we made a simplifying assumption that after a tile is picked from the bag, it's replaced. So the probability of each of the tiles remained constant. So the blank tile has a probability of 1/7, and the line, elbow, and 4 connected tiles have probabilities of 2/7. And now I'll give a brief overview of the probabilities we calculated for some hole types. So the first hole we studied was a 1-tile hole, and we found that 3 edges determine what single tile can be placed to fill a hole. So in this case, we can only place a line tile, so the probability of filling the hole, or the total probability of filling a hole, is 2/7. And then moving on to 2-tile holes, we started with the 1x2 holes. So in creating these probability trees, we decided that we would only place a single tile at a time, and that the probability of each branch would be the product of the probabilities of placing each tile along it. And the probability of filling the entire hole is the sum of the probabilities of each branch. So for this example, we begin by considering the tile types that can be placed in the hole. So here it's the line type and the elbow type. And then we consider if the tile can be placed in more than one position and assign branches accordingly. So if we consider the line type tile, it can be placed in both the left and right position of the hole. So we have branch A and B, and we assigned the probability of each of those branches as 1/2, just to reflect that there's an equal probability given the number of options. And after placing the first tile, we're left with a single tile hole with 3 edges determined. So we know only a single tile corresponds to like a suitably connected filled hole. And to calculate the probability of branch A, for example, that branch is the product of the probability of placing each tile. So it's going to be the 2/7 times 1/2 times 2/7, which gives us a probability of 2/49. And in this case, all of our branches just happen to have a probability of 2/49. So the total probability is 8/49. Then moving on to 2x1 holes. Since we decided that we can only place a single tile type at a time, we really actually just have 2 1-tile holes where all 3 edges are determined. So we'll only have a single branch in this when considering these hole types. So the lower branch, or the lower position, has to have an elbow tile, and the upper position has a line tile, and our total probability is 4/49. So our next step was considering like slightly more complicated hole structure, which is an L-shaped hole, which is composed of 3 tiles. And when we'll start this diagram like the same way we did the 2x1 holes, considering a single type that can be placed in the bottom or the left position in the L. After placing the first tile, we're left with either a 1x2 or a 2x1 hole. And luckily, because we, like when when we were doing this during our research, we had evaluated all the 1 and 2 tile hole probability trees. We were able to refer back to the previous probabilities we calculated in doing these holes. So we really just have to place the first tile to reduce the size of the hole, and then we can refer back to our previous calculations. And while studying these holes, we found that we could increase our probability depending on where we choose to place certain tiles. So here, for example, the probability of filling the 1 by 2 versus the 2 by 1 hole is different. So the player could increase their flexibility in the game. So it's important. So we decided that we could define 2 such probabilities given this option, and we decided that you could either have a random probability such that when we're given a choice as to where to place a tile, each choice has an equal probability. So the total probability for this example is 20, 40, and 40. I can't speak. 20, 340 thirds. Even though branch C has a lower probability. And then we defined a second type of probability, which we call the smart probability, where given a choice of where we could place the tile, we could discard the path with the lower probability and adjust the probabilities of the remaining branches to reflect our reduced options. So in this example, our total probability increases to 24, 340 thirds by taking out branch C and then updating the probability of branch B from 1/2 to 1. And there are instances, well, I proved that for L-shaped holes, we can increase the probability of by placing the first tile in the bottom of the hole, because the probability of filling a 1 by 2 hole is greater than or equal to the probability of filling a 2 by 1 hole, regardless of the boundary condition. And there are instances where the random probability is equal to the smart probability, which is really nice when doing handwork, so there's no extra thinking you have to do, but it's a consistent result that's helpful to keep in mind during gameplay, because it gives you it increases your odds of clearing the row with more ease. So here's a quick summary of the hole types we've considered thus far. The dotted edges indicate that the edge is free, so either there's no constraint on the edge or the hole is along the side of the board. And I was able to automate the, these probability trees in Python. So that was really fun and helpful because it was my first real Python project, but it's also handy when we complicate the hole types and we're studying larger holes. Doing the trees by hand is just really obnoxious and messy. Another really fun thing was, so in Tetris, a player can clear multiple rows at once, and we were curious if it were possible to do in Knotris. So I took some information about the boundary conditions that we got from the filling a row algorithm, and I applied it to our gameplay strategy for this proof. So in order to clear multiple rows in Knotris, there's a few guidelines we have to follow. The first being that the rows we want to be cleared during that move must be stacked, so they're all internally suitably connected and not externally suitably connected, because we want them to remain on the board. And here on the right, I have an example where the boundary condition I'm using is 1, 1, 1, 1, 1, 0, and it's not a special reason, it's just easy to keep track of. And it isn't the only boundary condition that can work. But to catalyze the rows being cleared, we need to place a row that is internally and externally suitably connected, the way we do when we're typically clearing rows. So we'll want the upper boundary condition we've been using to assemble these rows to be the lower boundary condition of the row that will catalyze the clearing. And the GIF on the right just shows I don't know, it's just satisfying to look at for me, what it looks like when multiple rows are being cleared. And this is just results that I had shown earlier about our boundary conditions and how that, like the options that we have when we want to clear multiple rows, like there's a plethora of boundary conditions to use, and it's like a perfectly viable strategy to like accrue points. In terms of future work, we published some of our work, and I'm in the process of getting a paper published, and I really want to work on creating like a more user-friendly probability tool where we can input more complicated and interesting holes and like see how the different ways you can decompose them and the probabilities associated, as well as creating an outreach tool. So folks who don't typically engage with knot theory can have like an entry point to learn more about this branch of mathematics, and also just like, I don't know, it's like a fun way to procrastinate low-key. So I'd like to share it with others. And I'd like to thank the conference organizers for like providing a space for me to share the research that we've done in our game, as well as our collaborators at Bellevue College, Ken Townsend, Eden, Andre, and Kellen. Yeah, that's, oh, also, yeah, this is here. If you would like to play the game, feel free to scan the QR code. And we have a article in Math Horizons that like goes a bit more into the mechanics of the game. And if you like, I don't know, if you just want to say hi, feel free to message me. Or if you have grievances about the game, feel free to complain, because we love feedback.